Well, good morning, everyone, or good afternoon, depending on which part of the world you happen to be in today. Welcome to the latest in the RISB webinar series. Today, we are looking at driving advice systems. So firstly, before we kick everything off, I'd like to acknowledge the traditional owners of the lands in which we meet today. For me, in WA, that is the Whadjuk Noongar people of Perth, and I'd like to pay my respects to elders past and present. I'd also like to extend that respect to any Aboriginal or Torres Strait Islander people who are with us today. Now, we've got a fantastic presentation all around driving advice systems. These systems have been around for a long time, or the creation of them has been around for a long time, and they've advanced significantly. So this is going to be a really interesting presentation on what they do, the science behind them, and what they can actually do for the rail industry. Today we have Scott Reimers, the Business Development Manager at Trapeze Rail, doing this presentation. Scott is a dynamic rail and transport executive with over 20 years experience in rail, including previous roles at Metro Trains Australia, Metro Trains Melbourne and Queensland Rail, looking into areas such as enterprise innovation, safety, learning and development, business performance and commercial. He has exceptional stakeholder management skills, is adept at team integration and has hands-on ability in customer-facing roles. Working for Trapeze Rail, Trapeze look at lots of different areas, mostly around modernisation of rail organisations and improving efficiencies, looking at things such as driving advice systems, workforce management, intelligent transport systems for light rail and trams as well. I would like to also acknowledge that we have Farbod Najedi here, who will also be assisting in this presentation. He is the Chief Technical Officer at Trapeze Rail. Just as a reminder, if you have any questions, please put them in the chat and we will get to those questions at the end of the presentation. I'm sure there will be plenty, so please don't be shy. Get your questions in so we can explore this a little bit further. But at this point, I'd now like to hand over to Scott and welcome to the presentation.
Yeah, thanks, Chris, and the RISB team for the opportunity to present today. Welcome everybody to today's webinar on Global Benchmark Driving Advice System Insights. It's also known colloquially as DAS, and that's how we'll refer to it during this presentation. So Farbod and I are excited to explore with you today how DAS is transforming the rail industry around the world. So whether you're new to DAS or whether you're leveraging its potential already, the aim of Farbod and myself is to hopefully provide you with some valuable insights on how the DAS technology is shaping rail future today and also into the future. So let's just get started. Before we dig into the content, there's three objectives I just want to tease out with you. And firstly, we want to focus today on proving the DAS technology. So we're going to dive into the key industry data points. We're going to have a look at, I guess, how DAS uses predictive algorithms and optimization and really try to demonstrate how advanced DAS systems are. Talk a bit about the science behind it and the physics behind the DAS system. We're then going to jump on to sort of unlocking the DAS benefits here, highlighting the key challenges that DAS helps to address. But also there's a few myths that I want to clear up, and I want to share some facts around the DAS system as well, so you're clear on what it is and I guess what it isn't. And finally, we want to connect this theory, these first two objectives, into practice. And we're going to have a look at how DAS works. We're going to do some comparative analysis. We're going to look at some case studies in Australia and globally. And this is where we'll spend sort of the last 20, 25 minutes of the presentation, really demonstrating how this technology enhances performance, safety, sustainability and real-world applications. So to start, I just want to, I guess, draw our attention to some compelling data points. So these are data points that we've captured from our clients and also are sort of around the globe from other case studies, and just talk a little bit around how DAS has a positive impact on the rail industry. So the next two slides showcases, I guess, six metrics, and these figures help us quantify the tangible benefits of DAS and how DAS provides a clear value to rail operators. And we'll reinforce these metrics. They'll become, I guess, hopefully true to life when you actually start to see the comparative analysis and you start to see the demonstration. But for now, look, I'm just going to go through an overview of the key benefits and talk around how DAS contributes to each of these metrics. So idle time, fuel consumption, DAS is about monitoring and minimizing that idle time. So DAS can reduce fuel wastage through journey planning and route optimization, and therefore generating both benefit to diesel and energy consumption. And you can see there's a couple of metrics there that are pretty much standard across industry, where diesel trains consume 1.3 litres of fuel per hour of idling. In terms of DAS, also recommends optimal acceleration points and coasting strategies. So you hear a lot about in this presentation around braking, coasting, and acceleration, three main points of DAS, and the benefits of actually minimising acceleration and hard braking and maximising coasting. So this strategy actually is about reducing the frequency of unnecessary accelerations and therefore conserving energy. And as I mentioned, braking as well. Braking too often can result in 10 to 20% increase in overall fuel or energy consumption. So DAS provides advice on braking earlier and coasting longer, and therefore avoiding that hard braking and therefore minimising that energy waste and saving fuel. In terms of coasting and energy efficiency, on the left-hand side there of the slide, you see DAS identifies ideal coasting opportunities. So through the journey planning and journey mapping, it identifies the most appropriate braking and acceleration and coasting points, and really helps drivers conserve between 10 to 20% fuel and or energy and extending the train's efficiency and effectiveness of operations. Optimal speed management, as I said, acceleration and managing your speed and make sure you have the optimal journey plan is critical to a DAS implementation, and reducing the speed fluctuations and therefore getting about 5 to 10% energy usage or energy saving and improving train performance. The final point around timetable adherence and energy use is an important one. Even though it's last on the list, it's important to finish with, because DAS's principal focus is providing advice to maintain schedule and timetable precision. So even though sustainability and energy efficiency is critical, it's really principally driven by ensuring we maintain timetable and to a schedule. And when we do that, we still do that by minimising fuel usage and overall efficiency without sacrificing availability or punctuality targets. So these 6 benefits I spoke about really are a direct impact to operational costs, savings, and train reliability. Looking ahead, we're going to revisit these metrics. We're going to examine them in a little bit more detail in the case studies, as I mentioned before, and you'll hopefully see, when you start to look at the comparative analysis, you'll see how DAS is actually driving a significant benefit across these data points. As I mentioned at the start, DAS uses a predictive algorithm, so it's worth taking a moment to kind of appreciate that hidden science. And I just want to talk you through sort of the aspects of that. Of course, we're not going to delve deeply into that science today. We've got a long-standing partnership with South Australian University, conceived in about 1999, and they lead our research into these detailed physics model. But what I wanted to do is introduce you to the fact that DAS leverages science. And when it leverages science, it then creates practical, impactful outcomes for the rail network. So what you see on the screen here just reflects the fundamental forces that engineers, train drivers, and operators work with every day. So as every train accelerates or decelerates and it navigates its journey, it essentially is a physics in action. So DAS is not just about the algorithms and software. It's not just about the outputs we give to drivers. It's built on the principles of physics that govern the motion. So whether we're talking sort of inertia here to keep the train moving forward and the role that it plays in acceleration and deceleration, or we're moving into talking about momentum, which is about the speed and the resistance to stopping, or we're talking about drag or friction and the impact that that has on train movement, every one of these factors is about optimizing train performance. So what you're seeing on this slide is just a representation of some of the key forces at play. And if I just quickly take you through each of these key forces, whether that's, as I said, inertia, whether that's drag, whether that's kinetic energy, potential energy, centrifugal forces, thermodynamics, friction, or momentum, all these combine to shape movement and the energy of the train. So by understanding these forces, DAS takes this raw science and transforms this into real-time actionable advice for drivers. And that really ultimately helps them balance operational efficiency and excellence, safety, comfort, and sustainability and fuel benefits. So as we move through this presentation and we start to get into the demonstration, I just want you to think about DAS as not as an innovation, but I'd rather want you to think about it that it's inherently tied to physics. And because it's inherently tied to physics and science, then it's got demonstrable proven results and benefits. So DAS is often viewed through the lens of energy efficiency, sustainability, and I guess rightfully so. When we put our business cases together with our clients, we start there predominantly, and then we move into on-time running and punctuality and so forth. And a lot of the business cases are based around the efficiency from an energy perspective. But DAS is more transformative to that, and I just want you to lift the lens a little bit, and I want you to have a think about how DAS can address more than one challenge. And this is what this slide really talks about. So there's a lot on this slide, but I want to draw your attention to kind of these outer circles here. These are sort of the 10 critical rail challenges that are facing rail operators globally today. And DAS provides both primary and secondary benefits across these. Green primary, yellow being secondary. So the multifunctional aspect of DAS is key to rail operations worldwide. And what I'll do is I'll quickly circumnavigate around the outside of this and give you an example of how DAS contributes to each of these key metrics or key challenges that sit within the rail operations. So first and foremost, DAS is about improved punctuality and availability metrics. It's about smoother rides. It's about reducing delays. It puts timetables and sectional running adherence first and foremost within design principles. And what we're seeing is in Paris, we're seeing improvements in on-time performance and customer satisfaction due to the deployment of DAS. We know, as I mentioned before, DAS promotes, environmental goals and sustainability. It promotes energy efficient driving. It results in reduced fuel. It lowers CO2 emissions, and it supports sustainability. Most of our business cases we're seeing is about 8 to 15% savings in diesel or fuel economy, and drives a strong business case. And that's what we're seeing globally. DAS also optimizes train schedules and spacing, helping rail operators manage more trains on the network, headway management without compromising safety. And you'll see when we talk around, what DAS is, junction scheduler, route rerouting support, provides support in capacity constraints. So we're seeing in dense metros, London, DAS has helped improve headway management. We've seen it reduce congestion, and we've seen it improve service frequency as well. DAS also improves safety, providing real-time advice to drivers and improving sort of the situational awareness that comes with those drivers as well. In Sweden, DAS has been credited with reducing overspeed incidences, SPAD management, and improving overall safety metrics, and contributing to lower incident or accident rates. And finally, regulatory compliance. Predominantly, this has been seen in compliance to environmental regulatory compliance, but also from a safety regulator perspective as well. So DAS can provide critical data for audits. It can provide data for reporting, and it's really been driven in the European operators at the moment, where they need to comply with strict emissions and energy usage. So they're using DAS to provide real-time and historical data to prove adherence to those regulatory requirements. So quickly, just sort of whipping around the outside in the yellow, DAS manages the strain on the aging infrastructure. It can help with minimising wear and tear. It can connect into OBD systems, onboard diagnostics. By optimising acceleration and braking, it can reduce braking, frequency. And, this is all about sort of extending the lifespan of existing infrastructure, as well as the rolling stock. It can support workforce skills and labour shortage by implementing an advanced training program, connecting DAS into simulation, getting real-time feedback for drivers, can make that more efficient, and drivers learn, driving techniques more quickly, and hopefully that can support, the addressing the workplace shortages. DAS is a critical component in terms of digital transformation. It can be integrated with digital systems like signalling, control centres, predictive maintenance, and it's really about fostering a more intelligent rail network. And we're seeing in Germany that DAS is integrated, it into overall operational control systems such as ETCS, ATO, and TMS, and so forth. Cybersecurity. DAS is all about deployments, including advanced cybersecurity measures now. So, it's putting in, PKIs, it's got encryption, it's all around making sure that, the data is controlled from a communication and a data perspective. And finally, from a cost management and financial, these 9 really drive that, reducing energy consumption, getting better in fuel costs, maintenance expenses, all contribute to better cost management and ultimately more financial viability across the business. So before I hand over to Farbod, I quickly just want to, look at some of the key facts and myths surrounding DAS. And on one hand, I've talked around how DAS can significantly enhance the operational efficiency, reducing fuel consumption and improving safety. However, there's some misconceptions that persist, and that can hinder the adoption of DAS and its integration. So I've just got 2 slides, and I'm just going to whip through very quickly, just so that we can clarify what is true and what isn't. And these are captured from, industry forums, and it's just worth surfacing them for you so that you can sort of understand the fact versus fiction. So I mentioned before, on-time running, punctuality, availability, metrics are a key benefit, and it's all about managing the pace of the journey. That's where we start our design principles, and that's where we lead our conversations. It can also be tablet connected to power and implemented in a phased approach. So it doesn't have to be tech heavy from an implementation perspective. It can benefit all train types, and it's also compatible with all rail networks. It's about enhancing driver decisions, giving them more data-driven insights, and giving them information to make driving behaviours. And it's also about measurable fuel efficiencies and punctuality. So as I said, it is science-driven, data-driven, and with that comes confidence that you're going to get measurable fuel efficiency, improved punctuality, and improved safety benefits. On the other side of it, it's really just the converse of what we just spoke about before. But some of the myths, as I said, it's only about sustainability. DAS does cover the top 10 critical issues that sit around rail operators at the moment. It doesn't need a lot of on-train integration. And I guess the point here around being cost prohibitive, most of our business cases we're seeing payback in 2 to 3 years. So it's, once you roll out DAS across the business, you're getting good payback and internal rate of return reasonably quickly. Obviously dependent upon, the network, take up time, driver adherence and all those sorts of things. But in general, we're getting good payback periods with our clients. As I said, it's about providing additional information to the driver, so not removing the control of the driver's actions, and not about implementing distraction. There's a lot of work that goes into it to ensure that it doesn't distract the driver, and we've got a good user interface that we can adjust and modify to suit the requirements of the operators. And as I said, it's not disruptive, and we have a range of technologies and a range of implementations that we can do, from short, implementations to longer implementations to phased. So, in terms of myths and in terms of facts, I just wanted to throw them out on the table so you've got a clear appreciation of what the industry is talking about in terms of those. So look, I know that was a pretty quick overview, but I wanted to allow sufficient time in the presentation for Farbod to demonstrate this theory and put that into practice. So I'm going to hand over to Farbod. We're going to spend the next 20 minutes. He'll delve into that real-life comparative analysis, use the theory we spoke about, and demonstrate to you how that actually works. So I'll just hand over to you, Farbod.
Thanks, Scott. Appreciate it. Hi, everyone. I'm Farbod Najazi. I'm the Chief Technology Officer at Trapeze Rail. So I wanted to go through an overview of some trial data that we have recently collected and conducted. I wanted to share with you some case studies from customers who are using DAS, and I also wanted to go through a simulation demo of DAS in action. So I'll start with the trial data. So this was a recent trial that we conducted with a metro operator in the UK. This trial was conducted in such a way that we collected data from the trains in operation, about 20 to 30 runs without DAS, and compared that information against the advice profiles that DAS would have calculated, or the driving strategies that DAS would have applied on that journey. This journey, you can see this is a lengthy journey. There's around about 24 or so stops, and it spans over multiple lines. So you can see that the distances keep increasing. The gray lines signify the actual train driving profiles that we collected. So this is the speed of the train versus the distance along the journey. We've been ignoring the, we didn't take into account the actual dwell times in between stops, because we were looking at the train in motion so that we can distinguish what the effects of DAS in that system would be. So the gray lines are effectively the journeys that was captured, or the actual journey that was captured. The purple lines are the worst driving strategy. When I say worst driving strategy, I'm talking about the fastest way that train could be traveling at while adhering to line speed. So if it was traveling at line speed, that's what the journey profile would look like. And then the aqua lines are the DAS optimal profiles. So this is what we would have advised that train, how we would have advised that train to drive. And the key point here is that the DAS does not compromise on the arrival time of those trains. So whether the train is driven in this fashion or in this fashion, it would arrive, the journey would still be completed within the timetable, which is what's defined here. Now, on many of these journeys, what's visible is that the actual driving profile is closer to the line speed, or the worst case driving profile that you see in the purple lines. And very few of these sections of the journey, the driving profile is similar to what the DAS would have done. There is one particular one here where drivers are driving similar to what the optimal driving profile would be, but the majority of them are driving to a kind of like a maximum speed profile, or a non-optimized speed profile. On the right side is the energy use that was calculated. These are electrical trains, so we had the traction energy measurements. Now, this is the traction energy for the overall energy use of the system, so it's not the tractive system specifically. But what we recognized was that the runs that were conducted without DAS were around about, typically on average, they were consuming around about 18 to 20% more energy than what was necessary to complete that run if it was being run with DAS. Now, over here we've got this is a fully laden train, so this is a full of passengers in that particular train, and this is an empty train. So the realistic, the average energy use would be somewhere in between. But even if we consider the worst case scenario of a fully loaded train, the majority of journeys that were completed, some of them took longer, but still managed to consume more energy than what a driving strategy of following DAS would have potentially produced. So that was quite an interesting trial, and I think it's probably worthwhile mentioning that the way DAS calculates this, maybe I should first mention that how DAS works is by maximizing the amount of coasting that a train driver can do in a particular run. So going from point A to B, how do you get from point A to B, but on time, but consume as little energy as possible? And you do that by coasting as much as you possibly can and reducing your braking and reducing your traction. What would happen in a lot of these journeys is you would have full traction. In this case, it's absolute 100% traction, and then applying brakes during this period in order to reach your destination. What DAS would do is apply traction, reach a certain point, and then apply a combination of traction and coasting along the middle part of that section, and then apply braking. And you might think, well, why isn't there a longer coasting period? Well, we still want to make sure that that train arrives on time. So finding out how much traction you need to apply in order to, and when you need to start braking is the key kind of, the crux of the algorithm here. So the way the algorithm works is it takes in 4 key parameters. It takes in the speed limits that are applying to that particular track. It takes in the actual track data itself, the elevations, the curvatures, the grades of that track. It takes in the timetable that applies to that particular journey, what the timing points are, and when the stops need to be reached by, and also the train specifications. So the power curves, the braking curves, rolling resistance, those kind of metrics. And some of them are fine-tuned during the configuration and the deployment phase. And given these 4 parameters, DAS can calculate an optimal journey profile, and that optimal journey profile is conveyed to the driver visually, either through a tablet device on the train or through the in-train display if it's integrated into the train display. And that advice typically has 3 basic forms: traction, coasting, braking. And we intentionally reduce it down to that level in order to reduce the amount of confusion for drivers on, what they need to do. The mentality that we're applying here is that if the driver adheres more or less to that speed limit, they might not get the absolute perfect run, but they will do significantly better than what they're typically doing in those journeys. So if I go to the next slide, let me see if this cursor is going to work. There we go. Okay, we've skipped 2 slides. Here we go. So this is another run similar to the previous slide. Again, we're seeing the majority of the parts of that particular journey are closer to the line speed than they are to the optimal, and that tells us that there is scope for energy reduction or optimization in how those journeys are being driven in order to get potentially 10 to 15% energy saving, while not compromising on arrival times, and in fact bringing a bit more punctuality, because that will help pace the journey and make sure that the train arrives on time. And I'll show you that in the simulation demo later on. So as far as case studies, so we have been working with KiwiRail. KiwiRail adopted DAS in I think it was in 2014. They had an ambitious energy target of reducing. They wanted a 20 gigawatt hour reduction by the year 2020, and it was an ambitious target by them for them, and they had that goal until 2022. They wanted to reach that goal, and what the finding was, I wasn't around in the company at that time, but what we've understood is they reached that target within the first 2 years. They reached the 2020 target within the first 2 years, and right now they are calculating around about 13% fuel savings attributed to DAS on their freight operations. KiwiRail is the New Zealand national freight operator. They have about 180 locomotives. They've got 350 drivers trained on DAS that are kind of on a daily basis using DAS, and they have a small team that is dedicated to ensuring the success of DAS in their operations, making sure that any issues are addressed, finding opportunities for improvements, and looking to kind of enhance the system and extend its capability throughout their organization. So we see a really kind of strong partnership with them, and more recently we've implemented another optimization solution on what's the best number of locos, or how do you conduct a journey and switch off locos at certain parts of the journey in order to further optimize your energy consumption. So where only one loco might be needed in a particular consist, when do you determine that loco should be switched off, and when do you switch it back on because you need that additional grunt or the additional power in order to complete that particular run. So KiwiRail has been definitely an interesting story for us, and probably one of the more interesting stories that I heard of KiwiRail when I first joined Trapeze was a previous colleague who was involved in the actual deployment of DAS in the early days, and he was telling me that they had DAS installed on the train, and the driver was doing their best to adhere and follow the trains to follow the DAS's advice. And I can show you, this is basically a visual of one of the forms of advice that we can show drivers. So this section here is telling the driver to apply tractive force, apply power, basically be in a high notch in order to maintain that speed. This white section is a coasting section, and this red section is braking until you to stop. And typically it's dynamic braking as opposed to air braking. But the interesting story that he told me was that they were on approaching the crest of a hill on a 750 meter long freight train, that had a weight of 1,400 tons. That's equivalent to around about 933 cars, which is a large parking lot in the city if you live in Sydney. Imagine driving a freight train and some system on a screen tells you, okay, now you need to start coasting before you reach the crest of the hill. 400 meters before you reach the crest of the hill, absolute, it's counterintuitive. You just wouldn't do it. And apparently that driver avoided doing that on the previous parts or opportunities of that journey that he was, advised to do that on this final bit of the run. And we've pulled out the same run and the same the advice profile that he received. So you can see here the train. That's depicting the train. It's around about 750 meters long. These are the kilometer posts down here, and this shows the rough elevation of the track. So you can see he's going up a slight hill on a very, very heavy train with, 2 DF locos pulling all of that mass behind them. And 400 meters before he reaches the crest of the hill, he's asked to start coasting. And, what would you do? Would you start coasting? What happens if you start rolling backwards? So apparently he did apply coasting at that time. And the train made it to the top of the hill, went over the hill, and you can see that the advice profile is forecasting that train would continue to coast and reach a certain point where you would need to apply braking. But the magic here is not only that the train needs to continue to go up that hill while coasting and make it over the hill and continue going, but the magic here is that DAS has calculated an advice profile that allows that train not to break the speed limits even after it's gone over that hill. So this is in the downhill part. After the crest of that hill, when it's going downhill, it's still not going to break the speed limit, and it's going to still adhere to the speed limit. So what ended up happening during that journey is about 11 kilometers of that journey were conducted fully while coasting, which is something the driver would not have intuitively done. And that's resulted in this was a short 30-minute journey, but roughly half of that journey, so 14 and a half minutes of that journey was just in this last part, coasting. And obviously, before that, there was a earlier part in the journey and there's significant coasting in that as well. But the entire journey, the full 30-minute journey, ended up being around about 72% coasting, 26% traction, and only this 2% braking towards the end. And of course, that's going to have an impact on wear and tear. That's going to have a huge impact on how much energy you're consuming throughout that journey, and while still arriving at your destination on time. And you could even argue that this train going 60 kilometers an hour could have probably started coasting sooner. That is true. It could have started coasting sooner, and it could have probably still made it over the hill. But it possibly may have been later at the destination if we had done that. So the calculation takes into account very carefully the fact that when we have a deadline and we have a destination to reach by a particular point, and so that's how the speed profile is calculated. So I thought I'd just go through that. Maybe that took a bit longer than I had initially envisaged, but that was an interesting story that I thought I'd share here. I should also mention that one of the key feedbacks that we have from the drivers in QRail is they really like the situational awareness that DAS gives to them, knowing the speed limits, TSRs, ESRs, different types of speed restrictions are captured into the system, and they also really like knowing where the back of their train is, and just the situational awareness, where crossings are, where certain landmarks and whatnot are, has been some positive feedback, which is not something that was originally intended, but it's a secondary benefit that comes out of DAS. I will move over to SNCF. There we go. So SNCF is the national passenger train operator. Actually, they operate freight trains as well, but we work with SNCF Voyageurs. They're the national carrier passenger train operator for France. They operate about 90 to 95% of passenger services in France, and they've adopted DAS in their operations fully, and they have a whole department dedicated to reviewing the results of DAS, making sure that it's being adhered to, tweaking, adjusting, improving, configuring, and so on and so forth. And they were actually using a program called OptiConduit, which is a French kind of interface with our algorithms in the back end. There's about 10,000 drivers. These are DAS devices that are deployed on tablets, and tablets are carried by the drivers and installed on the train. So there's no real integration between the DAS units and the trains. The tablets have simply a GPS that they have their iPad, so they use the native iPad GPS. The driver will get in, configure their journey, select their journey, and the advice will be provided to them. So SNCF is getting a lot of success out of DAS as well, and their biggest challenges right now is data management, reporting, and we're working with them on how we can enrich their data set. DAS collects quite a lot of data and metrics during these journeys, and they want to integrate this data with some of the data they collect in other places and create more richer dashboards that are going to help them make more informed kind of strategic decisions around their business. One thing that SNCF recently did is they conducted a study where they disabled DAS on several regions. I think in total it was around about 1,000 kind of DAS units were disabled in specific regions for a period of 2 weeks, so they can monitor the impact, or they can measure to see what the impacts of that would be. And they reported that they won't share with us the actual data. I'm not sure why. Very, very secretive of their information, but they reported just shy of 11% saving that was attributed to DAS, like energy consumption was increased, and the saving was attributed to being just shy of 11%. So that's consistent with what we had previously measured for them as well. But yeah, that was an interesting thing. I'm running a bit short on time. I might skip to the next slide. Scott, tell me if I'm taking too long, Scott. This is a demo of a simulation. We've recently integrated our DAS with a technology partner, Sogiclair, who are simulation providers for rail operations. So this particular simulation is a simulation of a rail service in the UK, Great Western Railway, and this is a very short video. We've chosen a very short stop, but I'll kick that off, and hopefully you guys can hear audio, and I'll just narrate through this. So the driver is configuring the DAS. They've selected the timetable. They're being shown what the train consist is, and this is going through really quickly, so I'll talk fast. They've got a due out indicator. This is the current time, and they're being told to this particular DAS is configured not to show advice at low speeds, so that's something that we've configured for this particular operator. And you can see that the train has been put into the highest notch in order to take off. The advice being shown to the driver, this is a text display, so we've got visual display, graphical displays, and also text displays for lower distraction. So they're being told to speed up to 65 kilometers an hour. I think this is miles per hour. So 65 miles per hour, and you can see the speed slowly building up and the train moving there. And the notch still here in this highest notch position. And the coasting advice is coming up in around about 7 seconds. So the person who's driving this let's just wait for the coast. So now we've been told to go to coast, and the notch goes into a coasting position. And in about 2 minutes, we'll be asked to start braking, or the driver will be asked to start braking. We're due to arrive at Tilehurst, which is the next stop at this time, and the ETA, based on the current driving profile, is expected to be around about this time. And this is showing the current time. The driver here is a systems analyst by the name of Romain in our team, and this is the first time he's driving a train. So you have to excuse him if he makes some rookie mistakes here. But this was just this is a demo, so we can see the kind of interface and what kind of information is conveyed to the driver and how they might act on that. So braking advice is coming in about 30 seconds. Now, again, this DAS is configured to disable the advice closer to stations as well, just to prevent distraction to drivers so that they can use their own make sure that they don't rely on DAS or be distracted by DAS when they're approaching stations. So you can see it was about 9 seconds away. So soon Romain is going to push this into a high dynamic brake setting, and you can see that train is slowly approaching its destination, which is further ahead, and the ETA is still within 3 seconds of what the timetable due-in time is. So it's quite nerve-wracking. I've done this as well, getting a train to stop. You're so used to driving cars that when you want to brake a train, it's like, oh, how do you deal with that? So it feels like it's going to stop any minute, but it keeps on going, and you can see that the arrival time is more or less on time exactly. Now, Romain overshoots the station a little bit. We can excuse him for that. But this was just a demonstration of how DAS gives advice to be able to arrive at the destination on time and maximizes the coasting. And you guys saw that in that journey, the majority of it was coasting. Now, one other interesting thing here is we're told the due out time, so the driver knows how much they need to spend dwelling at that station based on what the timetable parameters are that are being fed in. And then once the clock ticks, Romain is very careful. Initially, he was slow to take off. He took off about 10 seconds late. So DAS adjusted the profile to make sure he still arrives on time, because it's dynamically calculating, what the profile should be in order to get the train to still arrive on time. So if there's any unplanned stops mid-journey, or if there's anything like that, then DAS will recalculate and give a new advice profile. That's it, Scott. I think I'm on time. Happy to take questions at the end of this. Actually, I've got one more slide, right? So whoops, what's going on? Let's jump to the next slide. Whoops, there we go. All right. So this slide is the future of DAS. So we are enhancing and building on DAS. We're working with UniSA and actually a couple of other universities and industry bodies to build and enhance on our capabilities. One of the key enhancements is obviously the introduction of CDAS. Now, CDAS is a connected DAS that allows real-time changes, real-time timetable changes, speed restriction changes, all of those things to be fed into DAS so that the driving advice can be immediately updated as a result of those changes in real time. Another system that we are trialing in the UK is a system we call Junction Scheduler, which manages the approach of trains to junctions in order to reduce stoppage times. So this is about recognizing 15 minutes in advance that two trains are about to kind of arrive at a junction together, and one of them is going to have to stop. So what's the point of stopping for 5 minutes or 3 minutes at that junction when you can potentially coast leading up to that junction? So that is quite powerful because it will dramatically reduce the amount of time spent waiting at junctions, and it will also make flow of traffic a lot more fluid, and of course reduce energy waste in the meantime. Another involvement is in battery energy management and battery kind of utilization, where to recharge, how long to recharge for, how do we optimize that, and we're also working in Europe around peak power management, which is concerned with managing how much power is consumed at different regions by trains, and how to reduce the maximum power usage of a train at particular times when power prices might peak or certain kind of capacity constraint events might occur. So yeah, I think that's it from me, Scott. Thank you.
That is it. Just go to the final slide. Thank you. Thanks, Farbod. So just to close the presentation before we get into questions, I just want to leave you with, I guess, an analogy or a metaphor where, DAS is kind of likened to a bit of to a conductor, where you're harmonizing various instruments to create, a beautiful melody or a song or whatever the case may be. DAS harmonizes the aspects of train running. So whether it's the technology, whether it's the data, whether it's the operations, to drive efficiency and safety on tracks. So without a conductor's guidance in an orchestra, the music might play out of sync, in the same way that trains may face operational inefficiencies or waste of time. So if I just leave you with that, each of you guys and girls are sort of key stakeholders in the industry. You play an important role in sort of managing performance across the network. And I guess your engagement, insights, and willingness to adapt new technologies like DAS and other technologies that are coming in the industry is critical for the success of the rail network. So I'd just like to thank you for your time and for your attendance from both Farbod and myself, and hand over to Chris now for any questions you might have before we wrap up.
Great. Thank you very much, gentlemen. Very interesting presentation, and certainly as a former driver, 10 years of driving, I can certainly look at some of this and go, wish we had this when I was around, although some of it does seem very counterintuitive to the way that we were trained to drive, and maybe still are trained to drive these days. So we've got quite a lot of questions here, so I'll jump through a few of them as I can. One question was around the use of system in the freight tents. So have you used this much in a freight area, and how does it work in there? Now, I noticed that there's been a few questions too about multiple, different consists, and I see, Farbod, you've answered that one. So yes, it does work on different consists. But have you used this system much in a freight sense?
Yes, so KiwiRail is an example of a freight customer that we have, and yes, we do take care of multiple consists with that customer as well. So we can even adjust the speed profile mid-journey on a stop if they change the length of their train, or add on or reduce wagons, or unload or reload, so consist changes are taken care of. This is also true for passenger trains as well. Some passenger trains might have their consist change mid-journey, and we take that into account as well. Yeah, absolutely.
Oh, excellent. A question here, how would you signal using different lower notches? Let's say if a steady lower throttle would give a good result as opposed to a high throttle and then going to coasting. So would the system sort of consider that?
Yeah, that's actually a really good question, Chris. And this is something that this is one of the principles of. So this is consistent across all trains. What we find is the power ratio, the power to mass ratio at higher notches is always more efficient than at lower notches. So while you might think you're saving energy by moving at a lower notch, you're better off. Train drivers are better off driving at higher notches, building up speed, and then coasting. The overall net effect of that is going to be less. So that's one of the key principles of this system. So while we don't specifically say use a high notch or use a low notch, what the advice is effectively telling drivers is, when we're showing green, that the ask is that the driver applies a higher notch setting, because that's got the more efficient. So driving at notch 4 versus driving at notch 8, you're not consuming half the amount of power at notch 4. You're actually consuming a bit more than half the power. So you get the best efficiency at the higher notches. And that's why theoretically, the physics and the maths of this, we work it out so that we're relying on drivers to try to use the higher notches where they see appropriate. And then, coasting is coasting. Now, of course, there's also going to be effects of weather. There's going to be wind. There's going to be headwind, tailwind. All of those things are going to take effect. But it's really difficult kind of getting those inputs into this system in real time. But what we find is we take those into account when we do the drag coefficients and the rolling resistance coefficients. So there is some provisions in the maths in order to account for those.
No, that is really interesting. Yeah, the efficiency of locomotives is actually best at high power rather than at a lower power. So that is actually really interesting. Right, I'm going to have to try and pick out a couple of questions here. There's one here. Are the acoustic benefits with smoothing out acceleration braking being considered or been is there any quantifiable data around any improvement in acoustic benefits?
I'm going to have to take that offline, I think.
Yeah. It's a good question, Chris. Yeah, anything we don't cover, we can take offline and get back to the person that's asked the question as well. So,
because that could be an interesting discussion for built up metro areas, etc. By using a DAS system, does that actually reduce the acoustic signatures of the trains and reduce noise pollution, etc., etc.? So it'd be an interesting area to look at.
It's definitely like spending less time in traction is going to be is obviously going to be better for that. What we do know is that passenger comfort is definitely kind of improved, while gradual kind of increase of speed. So when we tell a driver to, or when the advice is telling a driver to speed up, in that demo you saw Romain kind of going straight from notch 0 to notch 8. That might not be the best practice. So we leave it to drivers to make their own decisions about how they manage those in-train forces and get to the speed that's advised. But the thought is that once they're at that speed, once they reach that speed, switching back and forward between coasting. So how they smooth between advice changes or mode changes, we leave it to the driver. We don't want to micromanage that. Drivers know what they're doing. We don't want to kind of get involved in that area, but the overall managing the speed, managing the pace, I think that's where the real benefit of DAS comes in helping arrive at the destination on time and minimize to the best of their ability the energy use in doing so.
Okay, I'll quickly ask you one more. Now, we've had a question here around safety integrity. So let's say that the driver is getting advice, but it might be incorrect and the driver follows that advice. And ends up, potentially, having a SPAD, a signal pass to danger or something like that. How are you establishing safety and integrity requirements around this?
Yeah, so this is a really good question and definitely worth talking about. So this was one of my early questions when I first joined the organization as well. And in the UK, in France, across some of the different operators, I asked them how they overcame this challenge. What if the signal is telling you to slow down, or what if you're facing a red aspect ahead, but DAS is telling you to speed up? Because DAS might not know what that signal state is. And the response that I got every time was, this has been marked as an advice system for that exact reason. This is providing advice, and drivers will know that you've got a red signal ahead and this thing's telling you to speed up. Well, no, you shouldn't be speeding up. So I almost kind of got the response that I got from some of the ex-drivers in the UK is, we're not idiots. We know what we're doing. We know that we need to stop at the red signal. We know this thing doesn't know about the red signals. Now, what we're doing to try to counter that is we are doing signaling system integration. So we're working on integrating the state of those red signals into DAS so that we can suppress the advice or potentially modify the advice to allow integration and reduce those particular conflicts. And also we've implemented certain mechanisms in the algorithm so that if the driver is doing something that's vastly different to what the advice profile is suggesting that they do, that the advice profile just disappears altogether and stops being a distraction. So we're building this system in order to be a tool and an assistive tool to drivers. And if we're going to be if the driver is doing things that's different to what we're advising, then we're probably, the driver is in the know. So we suppress that information and make sure that we don't cause any further distractions.
So yeah, obviously integration is the ideal solution. Look, thank you very much both for your time, and thank you everyone who joined the webinar today. Keep an eye out on LinkedIn and your emails for our next webinar when that's coming up. But again, thank you very much, Scott and Farbod, for the presentation, and I look forward to speaking to you all again in the very near future. Have a wonderful day. See you next time.
Thanks, Chris.
Thank you.
Thanks, everyone.
Chris. Thanks, everyone.